So, to underline the practical usefulness of pattern recognition and to tell you something that all the medical doctors don't know, and because it's loosely related to density estimation, I want to mention the following method. It is called multiple instance learning. Multiple instance learning is a description of a problem setting, and the particular algorithm that was suggested here in '98 is called diverse density. And conceptually, it works as follows: you have a feature space, and then you have bags of examples, and an entire bag is labeled as positive or negative, but if it is positive because it only contains a few members that lie in a particular point in feature space. Now, the practical application, of course, is to the so-called egg crisis. Yeah? So you could think of this, this is a two-dimensional feature space describing all the things that this person has been eating, and everything that that person has been eating, and everything that that person has been eating. And then here's one example of a person that did not catch the bacterium, so a healthy person. And so the question is, given such examples of positive bags and negative bags, how do you find the point in feature space that singles out the positive examples? Or here, it's the same example, but just a different representation. So here again, a 2D feature space. You see everything that person number 1 has been eating, everything that person number 2 has been eating, and you see that they've been eating all around the place, all kinds of different, they went to all kinds of different restaurants and so on. But, everything marked 1, that's everything that person number 1 has eaten, and number 1 caught the bacterium. The same for the person number 2, 3, 4, 5, and 6. However, you also see other people, those are marked by the black dots, that have also eaten all over the place, but they did not catch the bacterium. And so the question is, what distinguishes the positive from the negative bags? And in this particular case, it is the bean sprouts, or maybe not. So the headlines change from hour to hour. So here's an estimate of this so-called diverse density. So this surface here corresponds to the example that I've just shown. And this surface shows you at which locations in feature space you find all of the positive and none of the negative bags. Okay, so this would be the prime suspicion for what has caused the outbreak. Okay, and as I said, it's loosely related to density estimation. I just want to mention that this kind of problem exists and has been studied for a while. Now, as a second application, I want to mention nonparametric regression. So nonparametric regression using kernel density estimates, in particular the Nadaraya-Watson smoother. Which works as follows. The estimate at a position x in feature space is a weighted sum over the observations. normalized. So we have we're talking about regression. So in this case that I'm showing here, we have one explanatory variable and one dependent variable, and we want to estimate this functional relationship of y on x, and we take a weighted sum over all these observations y, where the weights depend on the distance to the current query x. So this is, the first is an I and the second is a semicolon. Okay, just make sure you can read this. Not a J, a semicolon. Okay. And so there are two ways of looking at this. You could either try and sketch here in this space the weight function, or equivalently, you could say that this weight function, you know, it can vary between 1 and 0. So if we only look at 3 different points, so the relative weight of the central point, depending, of course, on the exact kernel function, I should have used different colors here. So I'm now showing qualitatively the weight functions for these 3 points. At each position, they sum up to 1. And even though I assume that we've used a symmetric kernel, like for instance a Gaussian kernel here, we have a sharp transition and a smooth transition. The smooth transition occurs between these 2 points that lie close together, and the transition is halfway between these points. The hard transition applies if we are far from the respective points. So in this example, I've used the Gaussian kernel, and at this point here, let's say that the density of both this and that point have decayed already a lot, so both values are very low. But since we have this exponential decay, one of them decays much faster than the other as we move, and this is why we get this sharp transition here. Okay, and in this case, this is just something like a locally weighted mean. One can also instead use locally weighted linear regressions or quadratic regressions, which gives lower bias. And if you want to know more about this, this is explained in much detail in the book by Hasty, Tipshirani, and Friedman. Okay, and so we come to cluster analysis. So generally speaking, in cluster analysis, you try and find natural groupings in your data. And I'm showing you the example where I personally first came across this problem. So I used to work in a group where people ran molecular dynamics simulations of molecules like that or big proteins, and these calculations would run for weeks at a time, and you would get, by integrating these equations of motion, you would get many different configurations. And chemists and biologists, they wanted to understand what are the typical configurations. But all you have initially is just a hard disk full of data. So what can you do? You could try and visualize it. We have seen PCA. Or you can try and find representative examples. And this is one use of cluster analysis. So in this particular case here, there were millions of configurations, but out of these millions, the algorithm has picked out a few that are particularly representative for parts of the data. And here, in fact, each of these configurations is represented not by just one, but by the closest 10 or something members of the respective clusters. So generally speaking, cluster analysis has the aim of finding natural groupings in data. And that can be either a pre-processing step for visualization, so that you then look at one of these clusters in detail, or you can look at this as a way of lossy compression. Or generally a way of summarizing your data. And this is an unsupervised learning technique, so you use it when you have no labels, or if you're interested in the structure within a given class, so that the label is homogeneous for all observations. Now, one thing that's regrettable is that in cluster analysis, it is impossible to find just out of the data the true answer for what is the right number of clusters. And the example I always think of is the task of clustering the world. So if somebody asks you to cluster our universe, there are a couple of answers that we would all say are reasonable. You could either give galaxies as a result, or solar systems, or planets, or atoms, or perhaps elementary particles. And in each of these cases that I've mentioned, you have a lot of empty space between the entities. And without any additional information, you don't know if the desired answer is atoms, or if the desired answer, or let's say nuclei of atoms, or if the desired answer is galaxies. So in cluster analysis, you always have the user always needs to specify either the length scale of interest. So to say, if you're interested in a clustering on a nanometer scale or on a light year scale, or the user has to specify how many clusters he or she is looking for. If it's a dozen, or if it's hundreds or millions of clusters. Yeah, there are Bayesian methods where you can try and infer the correct number of clusters, but even these need a prior. And so I would argue that in cluster analysis, you always require a specification of either the number of clusters or approximate number of clusters that you're looking for, or of the length scale that is of interest to you. There is a host of clustering methods, and there are different ways of arranging them. You could, for instance, distinguish between clustering methods that are fuzzy or crisp. So how can we sort the clustering methods? We have fuzzy versus crisp. Fuzzy means that any observation can belong to more than one cluster center. Crisp means that each observation belongs to exactly one cluster center. You could distinguish between hierarchical versus non-hierarchical. So in a hierarchical method, you arrange your observations such that you obtain a nested structure with the guarantee that two observations that are decided to be within one group at a fine level of detail will always be considered to also be in the same group as you go to a bigger scale. And a typical way to represent such hierarchical clusterings is in terms of a tree. So I've taken a picture from Ernst Haeckel here, where this picture is no longer up to date. You know, the tree of life today looks a little bit different. In particular, people are no longer sure if it's really a tree or if it's not a more general graph. But in those days, so he distinguished between animals and plants, and I cannot read this. You know, some kind of low-level organisms. Okay, with plants, animals, and protista, whatever those are. And you see that in this case there are 3 levels of detail. So you could either cut here, and then you would get a distinction into 3 groups, or you could cut here, and you would get a distinction into, what is it, 19 or so groups, or you could you know, cut at even finer levels of detail. So in that sense, clustering methods are also a way of organizing information that you have, in particular hierarchical clustering methods, for which you can draw such a dendrogram. So in hierarchical methods, there is no rule that it must be such, but usually people construct binary trees and indicate the similarity between observations by specifying at what levels. And that's, I'm losing patience here, so this goes on. By indicating at what levels 2 observations become merged. So you have here a scale, and then down there the individual observations. And for instance, by just looking at the dendrogram, you could tell that this is probably an outlier, because this is a single observation which lies a long distance from all the other observations. Where long, well, that needs to be, that depends on, you could use Euclidean distance, but sometimes you have more prior knowledge and you could compute other distance measures. Now, in such a dendrogram, you can cut at different levels. So, for instance, you could cut here and you would get 2 clusters, or you could cut there, you would obtain 4 clusters, and so on. And the typical question is, where should you cut? And a good cut is at a location where the number of clusters is relatively stable as you cross the scales. So you would not want to cut here because, if you move up or down your threshold a little bit, there are many more or fewer groupings, but then there's apparently some region of stability where you could vary your threshold without changing your clustering result immediately. So there's fuzzy versus crisp, there's hierarchical versus non-hierarchical, or you could distinguish clustering methods according to how they represent clusters. So clusters could either be represented by a single member or really by the entire group itself. So when you work in a Euclidean feature space, then it's quite typical to have cluster centers that are taken as representatives for all of these members in that same cluster. But sometimes you're only given a distance matrix. And in that case, it may make sense to really specify the group itself without having a single member that is taken as a representative. So I want to spend the next hour or so on clustering methods that are density-based and hence relate to what we've seen before. In general, let's assume that we have already estimated a density. And given such a density estimate, you could now construct or conceive different ways of clustering your information. One way of clustering would be to say that you split according to the local maxima. So we could say that all of that and all of that. So this would be one possible clustering, a crisp clustering. And this would be according to the peaks or according to the modes of this density estimate. Right? Because these cuts are wherever they partition the density estimate according to its modes. Or you could think of you could construct a hierarchical clustering here by saying that could construct a hierarchical clustering in different ways. One way would be to cut the density at different levels. So for instance, if I cut down here, I observe one cluster, well, plus outliers, so this would correspond to this bar here. But as I lift my threshold above this point here, I now get a splitting into two clusters. And as I further lift my threshold, I eventually come to a point where I start to see two subclusters here, and so on. So this would be one way of defining a crisp hierarchical clustering. A different way to define a crisp hierarchical clustering would be to say that we compute density estimates that are more and more smoothed. So in the extreme case, I would just get a single mode, this would be here, and then as I decrease my smoothing filter or smoothing kernel, I would see two modes, and if I make it even smaller, I would start and see those local maxima. And finally, there's also a possibility to interpret this in terms of a fuzzy clustering, namely to try and estimate and say, assume for instance that this is a sum of three Gaussians. I'm trying to draw them here. So this would be a fuzzy clustering where, so some observations, it's pretty clear that an observation out here would belong to this Gaussian, but an observation in the middle, it's not quite clear if it would belong to the one or to the other. So this has been purely qualitative. I just wanted to show to you that there are different conceivable ways of creating clustering algorithms based on the density. And today we will discuss two of these, namely the orange and the green one. We start with the orange one and come to the green one later on. So in mean shift clustering, what you do conceptually is to first estimate or find the kernel density estimate. And to then do a gradient ascent. So to then walk uphill on this density estimate, starting from each and every observation. So you can think of your density estimate as a landscape, and you have hikers that start at the locations where you have observations. Each hiker walks strictly uphill, and those hikers that meet on a given summit, they form one cluster, they belong together. So points that are ending up in the same local maxima or in the same local maximum. They are members of one cluster. So in pictures, here's what's happening. On the top left corner, this is a true density. Down here is, and this is where samples or points that were drawn from this density. Down here you see a density estimate, a kernel density estimate. And now we can start at each of these observations. For instance, this observation was lying somewhere here. And then we walk strictly uphill. And if we do that for each and every observation, so we get one trajectory that starts at each of these black points here. So if we do this for each and every observation, we obtain parties of hikers that end up in the same point. So one party got caught on this low maximum here. An isolated party ended up there. Lots of hikers walked up this big peak and so on. So at the end we have, in this particular example, 6 different clusters. Now the trick in mean shift clustering is to not compute this kernel density estimate explicitly, but to directly walk uphill in this picture here. So in mean shift clustering, you start at any of those points, and you then build a weighted local mean of the observations that you see around yourself, and then you take a step towards that local mean, and then you iterate this. And if you do it, if you do just that, you end up with these trajectories. And the question is, what does this local weighing have to look like so that the result is the same as if we had walked up the density estimate? And this is what I want to show now. So the trick in mean shift clustering is to never compute the kernel density estimate explicitly, but still get the same result. So to put things into perspective, this is not as important as the kernel trick in support vector machines, but it's anyway, it's a nice algorithm, I think, and that's why I want to show it. And it's one that is being used in image processing a lot, which is not a good reason to talk about it. So the mean shift segmentation method in image processing is based on this mean shift clustering. So if we did follow the explicit recipe, what we would have to do is to compute the gradient of the kernel density estimate. And the gradient can be pulled into the summation, and I've omitted the 1 over n here. So this is the direction into which any of the hikers would walk if we followed this recipe explicitly. And the argument made by Yitsong Cheng is that it's possible to obtain the same results by using only a so-called local mean. So the local mean of a hiker that is at position x at time t in his hike is the sum over, so this would be local mean, Lm for local mean, is the sum over mean shift kernels that are located at all the observations. So you see, if you just squint and look at this formula, we have the positions of the observations in the training set. And so this is just a weighted mean of those observations, where the weight functions are centered at the current query point. And one can then make an update and say that the new position t plus 1 is given by this local mean, and the difference between the two, so the local mean minus the original position, that is called the mean shift. Now, if we want that the results are the same, so this is a direction taken by the hiker. So if I want this direction to be the same as that one, up to so the step size does not need to be the same, so up to some constant. This gives me a condition on how the mean shift kernels should look like. So inserting the definition here. And I'm going to bring this x onto the same fraction. Because the numerator and denominator here look very similar, I can write it like that. And it turns out that it's useful to rewrite the kernel in terms of a kernel profile. So we introduce a kernel profile. Where u is given by x squared. So the kernel profile is something like compressed version of the kernel. And then the gradient of x with respect to the kernel x can then be rewritten as the gradient of u, of the kernel profile of u, because with this change of variables times du by dx. And du by dx is just 2 times x. Okay, and so the gradient of x, p of x, can be rewritten as twice the sum of grad u of the kernel profile at ui times x minus xi. Where ui was defined as x minus xi squared. Okay, now we can this is also the expression that we had here. So overall, we can write, I'm now changing the signs. So I'm putting a minus here. Okay, we now have something that looks very similar on the left and on the right-hand side. I'm going to absorb this function of x into this constant to obtain, and the minus 2 I can also absorb in this constant. So I obtain a constant of x times the sum over I grad ui and that, if you now compare the terms on either side, that gives the principal result, namely that the mean shift kernel of x is proportional to the gradient with respect to u of the kernel profile of u. So if the kernel is chosen such that its profile fulfills this condition, then the mean shift result, or let's say the mean shift direction, is identical to the gradient on a density estimate that has been obtained with the kernel that matches this kernel profile. So the mean shift kernel should be proportional to the gradient of the kernel profile. And we can look at a few examples. So shadow kernel, this is the terminology used by Cheng. So if the Epernechnikov kernel were used for the density estimate, if you remember, this is the truncated parabola that is optimal for kernel density estimates. This corresponds to a mean shift kernel that is simply a box kernel. If we use the bi-weight kernel here, this would correspond to the Epernechnikov there. So the bi-weight is a kernel that has the third power. I'm not going to give the details now, but it essentially has the third power and the third power again, finite support. If we use the cosine kernel, so the cosine kernel is a cosine that has been truncated at minus pi and plus pi. Then the matching kernel would be the central lobe of the sink. And once more, the Gaussian kernel is special because it is the only kernel that is its own shadow kernel. So there has been a bit of so the algebra has been to show you that it's equivalent, but the real thing to remember is in this table. So if we use a mean shift kernel, if we use the box kernel as a mean shift kernel, what we would do is the following. We would start at some observation, and we would ask which other observations do we find in a ball around our given observation. Then we would compute the mean of all these observations and move our hiker to this new point. And then we would ask, putting a ball around this new point, which observations do we find and where is their mean? and we would move our hiker to that point, and we would keep iterating that until we end up in a local maximum. And what these calculations show is that the result of this procedure is identical as if we had first computed the density estimate using the Epanechnikov kernel and then performed gradient ascent on that density. It is unfortunately still a computationally expensive procedure because each move of each point costs order of n. So to find, we have to ask which points are in a neighborhood. So this costs us order of n. And we have to do that for all points. So that's already n squared. And then we have to repeat that multiple times until the points have arrived at a local maximum. So it's a computationally expensive procedure, you may say. However, it's one that has been quite popular as a low-level segmentation procedure in image processing, where the feature space is given by, on the one hand, the colors of a pixel, and on the other hand, by its coordinates. And in a paper by Komanichu and Meyer, it is described how you can use that to obtain some clustering of your images. And in particular for non-textured images, this works quite nicely. Do you have any questions? So the bottom line is, instead of walking uphill on the density estimate, we walk according to a locally computed mean, and the result is the same provided we use a matching shadow kernel and mean shift kernel. Okay, then we will look at faster clustering procedures after the break.